Hello, my name is Tobias Siems. I'm a postdoc at the Heidelberg University, working here in the Mathematikon. The following talk is a joint work with Lisa Köppel from the Tropical Institute in Heidelberg. And the topic is Metropolis-Hastings acceptance probabilities for mixture spaces. These are spaces with inhomogeneous properties, for example, changing dimension. And you might know that this really is an important topic. However, it turns out that the existing literature is quite divided over the abilities of Metropolis-Hastings in these cases, and therefore the following talk tries to clarify this topic a little for you, and I hope you enjoy it. Okay, we start with the general Metropolis-Hastings algorithm and how it works. Therefore, we are given a measurable space and a target distribution pi, which is the distribution we want to sample from. And then in the Metropolis-Hastings algorithm, the user has to define a Markov kernel K, which is called proposal, and he has to fix an initial state as nut. In step I, he proposes a new state S from K conditioned on the last sample as I-1, and then he would either accept S to be the new sample with probability A S-1 S, or he would reject and then take the last sample as the new sample. This procedure defines a Markov kernel mu, which is shown here, and it just says that with probability A S prime S, we will take S, this is the point measure centered on S, and with probability 1 minus A, we will take the last sample, S prime. Of course, pi has to be an invariant distribution of mu. This can trivially be ensured just by refusing to accept, because then if the last sample was distributed according to pi, the next will also be. However, in order to get a reducible Markov chain, we have to do a little better. So we consider the idea of TNA. He suggests using the measure psi, which is the sum of transitions in forward and backward direction. So from S prime to S and from S to S prime. And then we define the set R as those transitions where the density of the forward transition with respect to psi and the density of the backward transition with respect to psi are larger than 0. These densities are guaranteed to exist due to the Radon-Nikodym theorem. And what we get now is a symmetric set that represents the transitions which are viable in forward and backward direction. This set R now allows us to define another density, which is the density of backward transitions with respect to forward transitions. And it represents a density ratio for reversible transitions. And we can now choose the acceptance probability. We take the minimum of 1 and the ratio for reversible transitions and 0 otherwise. This would then achieve invariance of pi with respect to mu. And TNA could also show that this choice of acceptance probability is psi almost truly maximal over all choices of acceptance probabilities. So we can now speak of the Metropolis-Hastings algorithm. Let's consider an example, the Hamiltonian Mcmc. Therefore, assume that pi exhibits a Lebesgue density P over the R n-dimensional real space. Furthermore, we define an auxiliary variable U that also exhibits such a density K. We further assume that K is symmetric. With this, we can define the Hamiltonian as the negative log likelihood of S and U, together with the Hamiltonian dynamics. So we don't want to go into length with this, but the important point is that it introduces the time variable such that S and U are now functions of time. Therewith, we obtain a function Tu of S and U that is defined by following the Hamiltonian dynamics for a fixed time R starting at S and U, but with the difference that we flip the sign of U in the result. Altogether, we have now a proposal K, which first samples a U prime and then applies T to the last sample S prime and U prime in order to obtain the next sample candidate. And the theorem now says that the acceptance probability of this Metropolis-Hastings sampler is constantly 1, so we will always accept. This can be shown by verifying the following equality. whereby this is the Radon-Nikodym derivative between those two measures. At first, consider that the above integral can be expressed like this, where this is the exponential of the negative Eulerian, and this ensures that we transition from S prime to the evolution of the Hamiltonian dynamics. It can be shown that Tu is a self-inverse diffeomorphism with a Jacobian that equals to the identity matrix. This is a result of the Liouville theorem, and also the Tu keeps the Hamiltonian invariant. Here it's important that K is symmetric. So we can apply a change of variable where we replace S prime U prime with SU. This is the substitution. Then we flip those two guys, and we can skip the determinant of the Jacobian because it's equal to 1. And with this and the invariance of H under Tu, we get the desired result. This abstract definition of Metropolis-Hastings captures a vast collection of application scenarios. However, defining the acceptance ratio as a Radon-Nikodym density is impractical because the theorem only ensures existence but is not constructive. Therefore, in order to come up with acceptance probabilities that are feasible, we need to rely on densities for pi and k. Now let's consider families of disjoint sigma finite measure spaces. Here, pi would usually exhibit densities pi for all of these spaces, and if we are interested in the probability of an event in space I, then we would compute an integral over pi with respect to lambda I. This yields an overall density p of pi, which is defined as pi of s if s is in space I. This lives on a mixture space, which constitutes the union of all those spaces, and the superordinate measure lambda is the sum of all the sub-measures, whereby the identity here is just a necessary detail. Typical examples here are transdimensional spaces, where space I equals the I-dimensional real space. This occurs in model selection, where the number of parameters is unknown, but also in object recognition, clustering, and change point inference. We could use our Metropolis-Hastings sampler to simply sample across the mixer space as usual. However, in practice, these spaces are a bit more difficult to handle. At first, we want to address this by a modular design through mixture proposals. Therefore, we define a set of moves M, whereby each move exhibits a move probability QL that simply expresses the probability of choosing move L while being in S. Further, we have move proposals KL defined over the mixture space. With this, we can then define the overall mixture proposal K as the weighted sum of the move proposals. So we choose the move L according to Q, and then we transition according to KL. It is important to have for each move L its unique backward move BL. And Tierney could then show that in order to compute the acceptance ratio for move L, we just have to consider pairs of transitions in forward and backward direction, just shown here. However, if the support of the moves do overlap, then the maximal acceptance probability may not equal its pairwise counterpart. So this means that maximality is not guaranteed for mixture proposals. However, in a recent paper, Rodaki et al. Could give some conditions on when pairwise acceptance probabilities are maximal. They say that each move should exhibit its exclusive set of transitions, and that the move should only transition within the set. And all these sets should be disjoint. And then the second condition is that the set of transitions with respect to one move should be symmetric with respect to the set of transitions of the backward move. And in this case, we get maximal acceptance probabilities just by considering pairs of moves. And now, to make our life a bit simpler, we want to assume that for each move L, the set of transitions set L simply matches a pair of spaces. Now that we have explained mixture proposals, we should talk about transitioning between the spaces. And this turns out to be difficult in praxis because there is often no similarity measure available. Without a distance measure, we cannot perform a random walk. Furthermore, the variables within the single spaces may share complex relationships. That renders primal birth and death moves insufficient. And therefore we may end up with very low acceptance rate, and this calls for a more sophisticated approach. Our approach is to apply translation functions. These are functions that translate between spaces. And we found that there are two distinctive cases on how to translate. Let's assume we want to transition from Sj to Si in MoveL. The first approach is called ad hoc translations. There we define a translation from Sj to Si and a kernel density that acts on Si. So what we're doing is we translate the old sample into Si and then we apply the kernel density on the translated state. The second approach is called Postdoc Translations, and it's a bit more difficult. There we have to come up with an auxiliary measure space, a kernel density from Sj into the auxiliary space, and a translation function that translates the old sample and a state in the auxiliary space into this target space. So what we are doing is we first propose in the auxiliary space and then we translate into the target space. This can be nicely illustrated by means of these two graphs. So ad hoc translation, they use the translation function in order to translate from Sj to Si. And then they use a Markov kernel in order to propose in Si. Whereby postdoc translations, they first use the Markov kernel in order to propose in the auxiliary space UL, and they would then translate the old sample and the auxiliary variable into Si. Therefore, ad hoc translations allow us to freely choose the translation function as long as it goes from Sj to Si. They exhibit straightforward acceptance probabilities. However, the proposition must be carried out in the target measure space. And this last point is relaxed in postdoc translations because they detach the generation of random states from the target space. However, the problem is that transitions cannot be accepted directly based on P and K. That's because K does not live in the target space. It lives in Sj and Su and Ul. Therefore, the trick is to accept within the auxiliary space instead. The problem with postdoc translations is that they apply a deterministic function on top of a random state, and this would usually require an integral transformation, which might be difficult to carry out in practice. So we found a theorem where we give conditions on when to compute the acceptance probabilities based on P and K. So there we need first a new function UL from Sj UL to UBL, and then TU for MoveL should be a bijection, and the inverse of this bijection should be TU for the backward move. This is the first condition. The second condition uses a certain integral transformation expressed by f. So we take the push forward measure of the backward of the measures with respect to the backward move. We apply TU to it, TUL, which is then a push forward measure, and this should be equal to the measures from the forward move multiplied by f, by the transformation function f. So, and if this holds, we can compute the acceptance probability based on pk. So this term would be the common acceptance ratio, but we have to multiply by the transformation f. I found one paper that applies this in a discrete case. The discrete case is very simple because we can just explicitly compute the ratio, like here, and usually the measures are the counting measures, which means that this ratio is 1 anyway. So there's nothing to do actually. But for the backspaces, the transformation might not be so trivial. Peter Green dealt with this case, and he came up with the dimension matching condition, which states that the dimension of Sj and Ul should equal the dimension of Si and Ubl. And if the dimension matching condition holds and all measures are Lebesgue measures, then Peter Green found that we can apply a change of variable theorem here in order to find that Fl is simply the Jacobi determinant of Tu and L. Therewith, Green made a huge contribution to the model selection community, which is seen by those 5,000 citations so far. However, he made a little mistake because he concluded wrongly that his dimension matching is inevitable for transdimensional moves. And this caused a common misbelief that reversible jump has somehow enabled transdimensional sampling and that common MCMC techniques are not applicable in these scenarios. There are some papers that try to underlie this claim. For example, there's the paper from Carlin and Chip, cited 1,000 times, and they come up with an extremely complicated method just to avoid the transdimensional nature of the space. And they somehow argue with that transdimensional moves create absorbing states, and they cite TNA for their claim, but you can certainly not find that claim in TNA's papers. Then there is a famous book of Chen et al., and they say there is a lack of dominating measures, which is not true. Any countable set of measures is dominated simply by the sum of those measures. Then in subsequent publication, Green still keeps arguing about the limited capabilities of Metropolis-Hastings compared to reversible jump, but he also questions the approach of Carlin and Chip. So it gets a little funny, and if you look into the literature, you will find a lot of attempts to question each other, and sometimes people avoid questioning. They would just claim the opposite, and so it's also a little funny to read. But however, due to the outshining popularity of Green's paper, it is an ongoing issue that people still think you kind of have to apply reversible jump in order to go transdimensional. This brings us to the main question. What are actually the capabilities of Metropolis-Hastings sampler when it comes to Postdoc translations, or especially the reversible jump proposals? And I found a theorem that clarifies this topic, and it takes into account the fact that Postdoc translations accept in the auxiliary space, whereby Metropolis-Hastings sampler would only accept within the target space. And it takes that into account by means of an expectation. It draws the expectation of the acceptance ratio with respect to all values of U that yield the same transition as prime S. And therewith, we get the maximal Metropolis-Hastings algorithm for Postdoc translations. The two acceptance probabilities will not be equal. So if we look at the acceptance ratio here, we see that values larger than 1 will be clipped in the acceptance probability, whereby those values contribute nicely to the expectation. And this might be a reason to think that Metropolis-Hastings acceptance probabilities are still better. However, both are identical as long as the translation here given as prime is injective. And injectivity is preserved, for example, if the forward or backward move is a determinism. For example, if we move from a two-dimensional into a one-dimensional space, we can just take the average of the two values, and that would be a pure determinism. And I'd like to call such moves semi-deterministic translations. Let's illustrate that with a Gaussian change in mean example. That means the data is Gaussian with a mean that changes at change point locations. If the mean changes, it changes according to a standard Gaussian distribution. The time between two change points is geometrically distributed. And the data has a variance 1. So this is a transdimensional example because we don't know the number of change points. So we deal with a vector of mean values that changes its size. Let's start with an ad hoc birth and death proposal. A death is performed by removing a change point. That means we are collapsing two successive segments into one. And then we take the average of the data with respect to the new segment and propose a Gaussian around this average. In a birth move, we are adding a change point. That means we are splitting a segment into two. We would then average the data with respect to these two segments and then propose two new Gaussians as before. The reason why we are averaging is because the average is a maximum likelihood estimator for a Gaussian distribution. That means this translation function represents a partial maximizer of the likelihood. A postdoc birth and death proposal is a little more elaborate. In order to perform a death, we would again collapse two successive segments. Let therefore n1 and n2 and m1 and m2 be the length and means of the two segments. We would then propose deterministically according to this weighted average. This is again derived from distribution because if we assume that m1 and m2 are the maximum likelihood estimator of the two segments, then this weighted average would again be the maximum likelihood estimator for a new segment. In a birth move, we would again split a segment into two. We would then average the data for the first segment, propose a Gaussian centered around this average, and then we get the second mean deterministically by means of a symmetric reflection around M by using U. So this defines a diffeomorphism which with a Jacobi determinant that equals to n1 divided by n1 plus n2. The necessary shift and adjust moves are chosen equally for both proposals. Then both approaches yield reducible and aperiodic Markov chains, so the convergence against the invariant distribution is guaranteed. If we look at the acceptance rates, we see that for birth and death moves, both approaches are somewhat equal, even though the Postdoc translations are a little better. So we can conclude that the key to Metropolis-Hastings samplers is the feasibility of the acceptance probability. Those acceptance probabilities can be built in different ways. However, there's often a canonical choice, which leads to a maximal Metropolis-Hastings sampler. Mixture proposals may be applied conveniently in pairs. However, those pairs shouldn't be redundant in order to preserve maximality. Regarding the post-hoc proposals, we may conclude that they are highly sophisticated and allow for very tight adaptations. However, they are mathematically very elaborate and introduce strict conditions on the translation functions, whereby ad hoc proposals may realize very simple ad hoc-like translations. They are straightforward to implement and exhibit very simple acceptance probabilities. However, there's a point that needs to be considered. They still need to maintain a sense of reversibility because the translation in place in forward and backward direction should at least be close. They doesn't have to be a bijection, of course, but they should not be too far from each other because otherwise we will end up with very low acceptance probabilities. And therewith, I would like to thank you for your attention, and I hope you enjoyed it, and please don't hesitate to ask any questions.